Bonjour, I hope everyone is awake. I considered giving this talk in French just so that none of you would know what I was talking about, including the French people. But instead I'm going to give it in English and people will still not know what I'm talking about. This is work done jointly with the other lovely people on the slide here, Jonathan Anderson, Brian Kidney, who gave a previous version of this talk at BSDcon, Arun Thomas and Robert Watson. And yes, today is not the 23rd. Click. So what am I going to talk about over the next hour to try and keep you awake after having lunch? So I'd like to talk about a few things. Generally, when I give a DTrace talk, I give a bit of history of DTrace. In this audience, more people might know this than others. I'd like to talk about the motivation for the work we're doing with DTrace and how the group of us that you saw on the first slide are trying to use DTrace, sort of in broad outline, because that really underpins some of the changes we're trying to make to DTrace. I'll talk about some recent improvements that we've made to DTrace, both in our own private repos, which we will eventually upstream. Some changes we've gone into upstream, some changes have not. Some changes we think are more acceptable to a broader community, and some of them may not be. I'd like to talk a little bit about how people actually use DTrace, because I know this is not a room of only kernel developers, but the majority of kernel developers who use DTrace sometimes don't understand how normal people, you see the quotes from there? Normal people use DTrace, or less abnormal. And then I'll talk about, ooh, I said abnormal and the lights came on, because I need to be better lit. And then I'll talk about some future improvements and the changes we're planning to make as we continue to grow and improve the DTrace code. So this is my histoire obligatoire. This is my obligatory history. So DTrace originally developed by a company called Sun. Some of you may have heard of it. Back in 2005 was sort of the first public release that you could get in Solaris, but it was developed over time before that. First ported by John Burrell to FreeBSD in 2008. It's also been ported to macOS, so you happen to be running a glowing Apple. You also have you have DTrace, although it may or may not be completely enabled, in macOS. And since its initial ports, it has been maintained separately with some cross-patching between different versions. So I'll talk a bit about that towards the end of the discussion, but it's an important point to come back to because we have this open source code base that has been modified by different groups of people with some amount of coordination, but not with a ton of it. Okay, so what are the motivations we have, we being the research project I'm working on, also some of the people we've been working with in the community for using DTrace? And why do we care about DTrace as a technology? So DTrace is not the first tracing system ever built for an operating system. It is a quite comprehensive system, but I spend a lot of time working with people who are older even than me. And as far as I can tell, everything in computer science was done on the Atlas in 1953. So I'm sure someone will tell me that there was a tracing system on that. But one of the reasons that we're very interested in DTrace is because it's an extant open source system for tracing that is relatively well written and relatively easy to understand. And we believe that using DTrace, we can improve the state of tracing on large systems. So for those of you who've ever seen the title of my tutorial, the subtitle is No More Printfs, right? So what I would like to do is live in a world past the 1970s, where I don't have to use printf to debug everything. And I'd actually like tracing systems to be a pervasive, common feature of operating systems. Another motivation that we have in the research project is to expand tracing to distributed systems. And I'll talk about this a bit more in a couple of slides. But for those of you who've used the current DTrace, DTrace is usable on your single node. It's a very powerful system, but what if you could apply that to a distributed system? How powerful would that be? And there are distributed tracing systems that exist, but we believe that DTrace is a good base from which to build more distributed tracing systems. Now, some of us, Robert Watson and myself, have found that using tracing, we're able to teach about complex systems. So for this audience, that means we teach about operating systems. So when I occasionally teach undergraduates, because people are silly enough to ask me to come teach undergraduates, it seems like a mistake on their part, or when Robert teaches graduate students, which seems like a good idea, instead of making them re-implement some ridiculously simple device driver from which they will learn nothing about the operating system, we take them on a tour de force of the entire operating system using the tracing system. So a good tracing system like DTrace allows us to, in 8 weeks for Robert or in a week of full-time work for myself, take a class of 20 or 30 computer science students and show them how does TCP work, how does the file system work, how does memory allocation work. Let's show you what happens with locking. Things that take much longer when you're making them write C code from scratch. Now, of course, we all know that forcing them to write C code from scratch builds character. That's what we're out for. But we believe that tracing is really an excellent way to teach people about large, complex systems and to give them problem-solving techniques to understand those systems. So that's another motivation. We want DTrace to always be production ready. Sometimes it is. Mostly it is. And we want to do it in open source because, well, open source is good. Okay, so those are our motivations for continuing to push the DTrace technology forward. This is one of my favorite films. This is a film called Reservoir Dogs, which I have no idea how to translate that into French, but you don't, oh yeah, we just get to see a Reservoir Dogs with my terrible, terrible accent. So, another motivation. This is a crisis meeting, and I have been to these meetings, happily without the guns. So, when people debug real-world problems in large data centers or large distributed applications, usually there are 2 or 3 interested parties. So in this particular, this is called a Mexican standoff, by the way. In this particular Mexican standoff, it doesn't matter who is who, but you usually have someone from, let's say, this guy's from the systems group, they're the systems administrators, they keep the systems up and running. This old guy here is a mafia boss in this, but actually is the network administration group, and they're like, oh, they keep all the computers connected together. And then Harvey Keitel, who's my favorite character in the movie, he's the programming group. They're the people who actually take the programs and run them on the distributed cluster. And what happens is, usually Harvey over here sends in a bug report that says your data center, your massive compute cluster of 1,000 nodes or 5,000 nodes is slow. And then these 2 guys here go, no, it's not. And then they start pointing guns at each other, and bad things happen. Now, you'll notice there's a character lying bleeding on the floor down here at the bottom right. This is the actual consumer of the data who just wants an answer, but he dies first. So this kind of discussion and this kind of problem solving, by the way, the problem does get solved at the end. It does not go well. This kind of problem solving is really amenable to something like a distributed tracing system. Well, not the gun part. But actually currently, what we have in large distributed systems are uncorrelated data, right? So a switch generates some type of data, which is uncorrelated to what you get out of a server, which is uncorrelated to what you get out of a program. Wouldn't it be wonderful? Wouldn't it be a wonderful world if you actually had a system where you could trace all of that and correlate all of that data together to try and form a more coherent picture of where the problem is, as opposed to standing around pointing guns at each other and accusing the other one of breaking the system. So this is actually, well, I won't say that this photo, but this idea, and having been through these kinds of discussions with people, very loud discussions, are one of the reasons that I got interested in this sort of tracing arena. Okay, so I keep saying we. I'll mention the project that we're working on at the moment. This is Cadets, which is the Causal Adaptive Distributed and Efficient Tracing System. The idea behind Cadets is that we can look at all of the events, we can have transparency into a distributed system to answer an important question. Now, Cadets is a DARPA program, so it's focused on security. But the question we were trying to answer when something goes wrong in any system, but certainly something goes wrong in a distributed system, is also the answer to the question my mother used to yell at me when I would fight with my brother, which is who did what to whom and when. Right? And that is the question that you wish to answer in any sort of large distributed system. Who was the actor that caused the thing to happen, and when did it happen? Show me the ordering. So Cadets, because it's a distributed efficient tracing system, attempts to answer that, and we're using DTrace and that technology as one of the components here, another component called Loom, to try and give more transparency into what's going on a single node and eventually what's going on in all of the nodes in a distributed system. So there are two components to this. I will talk a lot more about DTrace. I will not talk about so much, I will talk about how we apply it. Mostly I'll talk about DTrace. We'll talk a little bit about Loom, which is work that's being done within LLVM to generate more in-program instrumentation. So let's get all that on the screen. So Loom is specification-driven program instrumentation. This will result in things like fat binaries. Of course, everything's built on FreeBSD because FreeBSD. And then we're using DTrace as our tracing framework because in order to have this transparency, we're going to use tracing. So how do we use DTrace? How does Cadets use it? So we use DTrace on a single node. We also leverage it for distributed instrumentation, which means we can have a single client that goes out to a large set of nodes and tells them to all perform certain types of tracing and then feed those trace records back to a central point. So this has some interesting side effects. So if you want total transparency into the system, you're not going to use DTrace as it was perhaps originally envisioned. DTrace was envisioned as a way of debugging a problem at the time. I have a problem, I'm going to go look into it. But if you're building a system that's trying to build up a set of records that gives you total transparency into everything going on in a system or a distributed system, then it's not turn on, turn off, it's always on. So in our project, we call this always on tracing. There are some side effects to that relate to doing security work, which I won't go into in depth, but it does mean that there are parts of DTrace that can be exploited by an attacker against us. We have to worry about that. And it also means that this is, to some extent, a novel way of using DTrace. People have certainly built full telemetry systems on DTrace. The Fishworks folks did that. I know that people at Isilon have done things like that. The FreeNAS folks do that. But they're not looking at everything in the system all the time. They're looking at subsets, and that is different than trying to trace all system calls or all of the interactions between programs in a distributed system. So that requires some improvements. Okay, so safety first. So one of the things that's important to understand about how we use DTrace and how we would like to improve DTrace or move DTrace forward, you have to go back to the DTrace design principles. So when DTrace was originally built, it was built so that it would have no overhead when not in use. And people seem to miss the last part. They're like, oh, it's supposed to be free. I'm like, at some point you have to execute an instruction no longer free. But the idea is that when you ship a binary, you ship a single binary. You don't have a debug binary and a regular binary. You just have the binary. And then if you don't turn on tracing, then the overhead should be 0 or very, 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 very small. That's by the way, a scientific measure of very, 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 very small. Really important, don't panic the kernel. Because it turns out if you turn on your tracing and the kernel panics, people get really, really annoyed, especially if you do it to them in production. Unless they're Twitter, then it's okay. And you have to protect the kernel at all costs. Well, this has some side effects on things you can and cannot do in DTrace, which we then have to think about as we apply DTrace to our workload or add new features to DTrace. So in particular, for those of you who've ever programmed in D has no loops. Because if you could shove a loop in the kernel, then it might loop forever because it turns out Turing, period. So no loops, there are no basic blocks. There are a bunch of things that, as programmers, we kind of expect out of a language that don't currently exist in DTrace. And for the most part, they don't exist because the designers of DTrace were trying to make sure that the tracing system they added to their kernel, to Solaris, couldn't either accidentally or maliciously be used to cause the kernel to crash. It turns out when the kernel crashes, so do everybody's programs, and people get cranky. Safety first. So D, the scripting language, is like C, but safe. The problem is that we need some of that safety to possibly be off. Another bit of background about DTrace, and I figured I'd put this in here for those who actually work with it. So DTrace was built on or about 2005. It was a simpler time with smaller memories and slower CPUs. This is your grandparents' computer. Not really, I mean, my grandparents were not born in 2005. But thank you to the Wayback Machine for keeping all of the marketing material of every company for the last 20 years, because when I want to talk about what a computer was like in 2005, I just go to the Wayback Machine. So this was, if you bought a Sunfire V890 server in 2005, you could have up to 64 gigs of memory. I think, I probably don't have that much in my phone, but I could. So, not a lot of memory. And this was, Sun hardware was nice, top of the line, high quality stuff. If you went and bought a Supermicro at the time, you could have up to 16 gigs of 400 SDRAM. I don't know why it's SDRAM. And, not a lot of memory, slow cards, etc. 3.6 gigahertz, 800 megahertz frontside bus. Now you wouldn't even bother putting this in a data center, right? So that means, what do I have to keep doing that? So sometimes when we apply DTrace on a running system using the original defaults, we run out of steam. Yes, this is Montparnasse. Yes, that train really did go at that station. So for those of you who use DTrace in anger, you've seen things like this. And please don't tell me DTrace is broken when that happens, as some of you have. DTrace is not broken. It's actually working as it's designed to work. Remember, going back a couple of slides, safety first. Right? If we're going to tell the operating system kernel to start recording events about everything that's going on in the system, we are not going to block on all of those events. We're going to have a ring buffer. It's a thing. We're going to have a ring buffer, or we're going to have some sort of buffering system whereby when we get behind, we're going to be like, okay, I can't keep up, so throw away some records. The DTrace is not broken. But it is a bit mistuned at the moment. So there are 3 tuning parameters: buff size, which currently defaults to 4 megs, and was, for reasons that I've never understood, severely limited on FreeBSD, but we've changed that by a tunable. So if you're having a lot of drops, you can try increasing that. The switch rate, which says how often we're pulling buffers out of the system, which defaults to 1 hertz, which you can increase, again, if you have a bunch of those drops. And lastly, so again, DTrace, built for safety, built in 2005, smaller memory time. There's 2 main memory sizing things. One is buff size. The other is the dynamic variable. So you might see this, 103 dynamic variable drops, which is different than the buffer drops. So you might want to increase this as well. Now, okay, so now you might say, well, it is 2017. Why don't we just make all of those bigger? Well, it turns out that DTrace, especially DTrace on FreeBSD, runs on a wide variety of platforms. In fact, it runs on some embedded platforms as well as servers. So we can't have a one-size-fits-all. We actually do need tuning for them. So let's talk about some improvements that we've made to DTrace, we being the Cadets project. So the first one we did was machine-readable output. So DTrace was built by people who loved awk. Now, I know we all love awk. I love awk, it's okay. But the output that comes out of DTrace is not easily parsable by programs, and generally it's not meant to be. It's meant to be parsed by a human who's looking at the console, or maybe they built a flame graph, which we will hear about later, but it's not really meant to be ingested into another program. It's meant to be sort of read over by anything. So one of the first things we added was libxo support. So now you can have your output in XML. You're welcome. Also JSON. Because we want to be able to build tools that consume the data from DTrace. We've added some new providers. There have been providers added by other people in the community. So one in particular is Audit, Mac and Mac Framework. OpenCrypto now has a provider. So does SCTP, which is a transport protocol, the XBB stuff. So as the code has been adapted and adopted by the community, we've added more providers to the system. And providers are just a way of collecting trace points together and expressing some form of functionality within DTrace. The other thing we've started doing is performance analysis. Now, going back to a much earlier slide, DTrace is nearly free when it's turned off. And people will then immediately ask, well, how much does it cost when I turn on a single probe? And the answer is, we're not really sure yet, but we have someone doing a PhD about that. So we've started to do quite a bit of performance analysis to see where we can do improvements so that when we're doing always on tracing, and there's a ton of trace points enabled at all times, we actually don't have a ton of buffer drops or other performance overhead problems. So we're doing that analysis now. We've also started documenting quite a bit of the internals. So the Solaris folks wrote great code. Go and look at the include files. They have really excellent comments, which I really appreciate. But they are not written in a way that you could then take a specification and, for instance, do a clean room implementation or explain to someone simply how they would do extensions. So we're doing that. So the comments explain the what. They explain a little bit of the how, but none of the why. So machine readable output. This is a simple DTrace one-liner, and you say something like, "Oh, hey, tell me when a syscall, when write fired," and bang, bang, bang. You get a bunch of text output. If we tell it we want JSON output, we get this nice little object that can actually be parsed by something that reads JSON, right? So you're not, well, people aren't normal, but normal people should not read this. It should go into a tool. So the JSON output gives us the ability to do things like give a timestamp to every event and separate the things that happen, like this is a function and this is its name, into their separate elements. And this is done automatically. So instead of having to write a script that converts something from text into JSON, we just spit it out, and then we can feed this into tools that can do analysis for us. Remember, part of our overall goal in the Cadets project is to deliver a system that can be used by security analysts to look at what's going on in a distributed system. Security analysts are not going to read this. They're not going to read this. We're going to build tools out of it. So, machine readable output. We've made a few improvements to the D language. So have other people. Actually, some of them have been imported by people in this room. So what is D? D is a C-like language that supports all the C operators. It is really structured like awk. Has thread and clause local variables, subroutines to handle common tasks, but you can't write your own. So we've started doing a series of improvements to make D do more of what we want. One of the things we had to add was a way to get at mbuffs. So if you're working in a distributed system, it's fine if you know about socket connections and you can see TCP and all that stuff. But sometimes you want to do packet inspection on packets that are coming in or out of the system. And in FreeBSD, we have mbuffs, which are a complicated but very useful method of encapsulating network data. So this allows us to read chained mbuffs in D. It's really important for all of the BSD-derived systems. So for those of you who are attempting to port DTrace to the other BSDs, NetBSD, OpenBSD, you probably want something like this because it does not exist in the original Lumos/Solaris code. There we go. And that allows us to do this cute little trick. So on TCP input, I've got an mbuff. I happen to know that it's in this 0th argument. And it doesn't matter if that mbuff is locally stored or in a cluster. And the script writer, which is the person we want to enable with this, just calls this one routine and gets a pointer back, and then they get this, I call this nice output, but then I'm a kernel programmer, so I'm a terrible person. This is the IP packet. You can tell by the magic 4.5 byte at the beginning. So this gives people using FreeBSD, and if the other BSDs adopt this, easy access to network buffers. Right, we needed this. So what are some other things we'd like to see? Turns out programmers really like if statements. And D has this ternary operator. I usually defy people to tell me what this is, and someone can email me the answer. I'm not going to leave it up that long either, so I'm going to make it difficult for you. Ternary operators are fine, but they're not great. So if statements improve readability. Remember, we want analysts to use tools, but we also have to have people to write analysis scripts in D, because those D scripts are going to be distributed to the entire cluster or whatever it is. And we'd like people who write in modern languages to be able to write some D. So the Solaris, actually, I guess this is the Illumos group, did a syntactic sugar version of this. So for want of an if, I'll make it just fill in. So this is an if block in a D program. This is the source code. And the way this works, one more brace. This is from Matt Ahrens, who did the work of doing the syntactic sugar version. So this is what happens when you compile this. Yep, goes out the bottom of the slide on purpose. So what happens is it actually just blows out the script to still have a much larger D script that sort of encapsulates your if. It's not a real if statement. It is sufficient for simple scripting, but it is not what we want long term. So I mentioned other things we added. So in the Cadets project, we are using audit, the audit subsystem in FreeBSD, to audit the system as it runs. And we've added an audit provider. So this is a subsystem for logging security-related events. It was originally done for the US government's Common Criteria Security Standards. It's been optional in FreeBSD since 2004. This is work done by Robert Watson and others. So we know what a provider is, DTrace code that collects together a set of trace points. What does this one get us? This gives us access to the whole audit framework. So that means we can turn on audit, and then we can use D to filter the data and get statistics, which we would have to write special programs to get from the audit records. DTrace performance. So I talked about tuning earlier, but tuning only goes so far. There are components of DTrace that are not as efficient as they could be. So for instance, the D compiler that takes the source code and turns it into D bytecode that gets executed in the kernel is not optimized. I wouldn't call it a pessimizing compiler because that would be unfair, but it is definitely not an optimizing compiler. So the scripts themselves generate bytecode that is not as efficient as it possibly could be. So the idea is that the idea behind DTrace, of course, is that it shouldn't degrade performance. You'd like it to not degrade performance too badly while in use. Now, one of the nice things about working on a DARPA project, when we first started working on it, I asked, as one of the engineering types as opposed to a research type, like I just write code. I don't know how the research thing works. I was like, well, how much penalty are you willing to pay to get transparency into a distributed system? And they said 100% overhead would be all right. I'm like, wow. Okay, give me your money. But it's still our goal that when you turn on DTrace, it doesn't make the system very slow. So right now, when DTrace gets behind, it drops records. The kernel can kill the tracing under high load. So one of the other protections that DTrace has against someone asking for too much data is that if DTrace sees that it's getting behind, it'll just kill the kernel. The kernel side will just kill the user side and be like, no, too slow, go away, and then the kernel will recover. So there are some, what are the possible solutions to dealing with this if we want to try and get every record? So if you think about a security application of a logging system, in a security application, you never want to drop a record, right? But if you never drop a record, then you will block all forward progress on waiting for something to happen, like writing the record to a disk. So we can look at things like changing our monitoring cycle. We can configure the buffer sizes. We can improve the decompiler, which is one of the things we're doing now. And then we can look at the efficiency of the underlying decode, both in the kernel and in user space. We can JIT the bytecodes, and we can leverage LLVM. This is one of the areas in which we're doing a lot more research. Jonathan Anderson is doing this with the Loom work, which is related but not completely the same as the DTrace work. But we believe that we can use LLVM and apply some of the, as a compiler toolkit, to apply it to some of the problems in D. So I keep mentioning Loom. Here's a quick aside. So Loom is an instrumentation framework based on the LLVM toolchain. What it does is it puts instrumentation directly into the intermediate representation generated by LLVM. The instrumentation is defined in their own policy files. The instrumentation can be done at any time as long as the IR is still available. So that means you can ship a binary and then add instrumentation later, as opposed to currently, in a DTrace context, you might have to add a statically defined trace point to get at something, or if you're in user space, you're simply going to be tracing a particular instruction if you guess the right instruction. The idea with one of the things we want to do with Loom is actually make it talk to DTrace in user space. So this required another change. So USDTs work kind of like this. We've got a provider file. We get it included. We compile that. We compile a couple other bits, and we get this binary that comes out. With Loom, unlike with USDT, the fat binary that comes out of LLVM can be instrumented later in the field. So USDT performance is similar to the kernel performance. So we do this NOP replacement, we do overhead. So, but there's some problems with this in terms of shipping the code, which is why we're doing the LLVM trace. That's that the DTrace tool is modifying the final binary. It doesn't leave it aside so that you can modify it in the field. It doesn't play well with make, I'm told. Relocates quite a bit of things. So we're adding this Loom-based userland tracing, where we just take a simple C file, we use the compiler to generate the fat binary, and then we ship the app, and then we can actually have a provider.d file that can be moved later in the field, and Loom will actually weave them together to do tracing. So we're currently working on this. We have a prototype system called DTprobe because we want to be able to call probes from a user space program. So we added a new system called that is not in FreeBSD yet. But this is used by the Loom system to do instrumentation. No change to the binary when there's no instrumentation, and it could be completed. So some testing, provider generation. Damn, I got to that slide too soon. Okay, so that's kind of what we're doing with Loom. If you want to know more about Loom, I'll point you at the work that Brian Kidney and Jonathan Anderson are doing. Now, okay, I've given away this slide. There can be only one. So I pointed out that DTrace was not the first, and wasn't even the only dynamic tracing system that had ever been built. It turns out some people on another operating system have built a tracing system based around BPF called eBPF. Using eBPF at the lowest level is like programming an assembly language, which for this crowd is like, yeah, that's fine. But for everybody else is like, why would I do that? But, things improve over time. eBPF now has DCC, a C-like front end. And more interesting to me, actually, is the PLY work was the Python front-end. So one of the real downsides of D is that you still had to be relatively conversant with both the kernel and user space to write big effective D scripts. To write D one-liners is not so bad. What you would like in a trace language is something more like the languages people use for scripting, like Python. Thank God they didn't use Perl. Yeah, I'm going to get that one in every time I give a talk. So you want something like Python, or maybe you'd like Lua, but you want a higher level language that gives you something that's readable after 15 minutes. So DTrace now has competition from eBPF and all of these other things, BCC and PLY, which are built on top of using eBPF. According to someone who actually is in the audience, and we'll be talking later, eBPF now has feature parity with DTrace. So we've got serious competition. There cannot be only one. So I mentioned the history of DTrace. How does DTrace get developed? So this is the current source flow of how code moves between various systems. You'll notice there's a Windows port. I haven't run it. Terrifying idea. But the main current users, and I guess I'll have to add OpenBSD to the slide eventually. The main current users of DTrace, macOS, Illumos, and FreeBSD sort of share code amongst each other. The original import was here. We continue to import some stuff. macOS pulls things from us, and I think they also get stuff from Illumos. We send patches back. There is a Linux port, which, whatever. They'll never accept it. But I'd like to make them accept it just to do it. So the source sort of flows between various projects, but there's no one project that can really be the ultimate upstream. Most people are still looking to Illumos to be the ultimate upstream, but we'll see how long that lasts. So what are we going to do next? This is an animation. How does that work? So we're proposing to do Open DTrace. I will not put episode 4 on the slide. A New Hope. So the idea is to have a cross-platform. It's already relatively portable. We're using the same RFD process that Joyent and Sun used to do requests for changes. It's already in an organization, and we've been. This is where we've started to put all of the stuff that relates only to DTrace. So changes that still need to go into FreeBSD still go into FreeBSD head. Over hopefully a short period of months, there will then be a source base in Open DTrace, which will be feature parity. We'll have feature parity across all of the operating systems, and will be importable by any operating system that wishes, which is going to be a big and interesting job. And people who are interested in hacking on that should come talk. So I mentioned earlier the specification. So, I know room full of programmers, nobody wants to write documentation, but it turns out to be really useful. So what are we specifying? Diff, DOF, and CTF. These are sort of the three major components. The data structures, the things that make DTrace go as a system. We're improving the testing framework. We're supporting new execution substrates like the JIT. That's why we write the specs, so you can actually figure out how to write the JITs. Makes it easier to do future extensions. Right at the moment, someone who wants to make an extension goes and looks in the source code, they think they know what's going on, and then they add something, and maybe it works, and maybe it has a terrible knock-on effect. Also, it allows for clean room re-implementations. There's at least one attempt to re-implement the CTF tools, which was discussed yesterday, where due to let's call it a license allergy. People wish to not use the CDDL code. They want to have a clean room re-implementation or something like that. So if we write the specification correctly by reading the code and testing a bunch of stuff, not only do we have a way of communicating to people who wish to extend or build on DTrace how to do it, but if people want to re-implement a new version from a clean room, they can do it. So what are some of the things we want to do as we move into the Open DTrace future? I'd like to have basic blocks in the D language if we're going to keep D at all. Bounded loops. Turns out programmers like loops, but it turns out they're also super dangerous. So bounded loops. It'd be nice to be able to include one D script in another and have them refer to each other as modules. Programming languages. Improve performance, not just because the project I'm working on needs it for always-on tracing, but because it's good overall. If you want to build a really impressive telemetry system for some sort of storage device or some sort of network device, you're going to need higher performance out of DTrace so that the DTrace, the tracing system itself, isn't stealing all of the cycles from the actual application. Improved test suite, we always want more tests. More OS ports. So one of the interesting things about working on the DTrace source code, it's well written, it's portable, if you mean portable to two architectures under Solaris. Now, it was ported to FreeBSD, very clever, ported to macOS, very clever, but we'd like to see more OS ports, in particular a port to RTEMS, which is an embedded system, is being planned. And I think doing a port to Linux will be fun because it'll annoy the Linux people. More architecture support. So again, it was quite portable to the two types of systems that Sun sold at the time, which was Intel and Spark. Someday I will pull Spark out of the FreeBSD tree, and then I'll be happy. But we would like to, on the FreeBSD side, we've already ported it to PowerPC, ARMv32, ARM32, ARM64, and MIPS 64, and we want to, and RISC-V, work done by Ruslan. So we want to make sure that that architecture support continues and that the system can support, more architectures as they appear. Finer grained libraries. So it's quite possible that we will tear up libdtrace into components that make it easier to put it into programming languages. That way I can have my PLY like Python that talks to DTrace instead of having to write my scripts in D. And we want it to be, the goal of fine-grained libraries is usable from other languages. So it'd be great if I could write Rust with, have Rust talk to DTrace, or Python, or Lua. I heard there's a thing called Go. Python, Rust, Go. That's weird, I'm missing a picture. Oh, there it is. Animations in the wrong direction. So when we talk about multiple architecture and multiple systems and the kinds of things we're going to have to do to keep DTrace working, so in the Sun world, and if you go back and look at that, it was quite a trip down memory lane to look at the Wayback Machines, what could I buy from Sun in 2005? Actually, I couldn't buy anything from Sun in 2005 because everything on my page was super expensive. But OpenDTrace, because it's going to run on multiple architectures and multiple systems, is going to run across a spectrum of machines, and it currently runs on all three of these as far as we know. This is a BeagleBone Black. This is what Robert Watson teaches on. This is a PS4. This is a machine that half of you have on your desk in front of you. So there you go. So OpenDTrace needs to be able to run on a spectrum of machines, from small memory to large memory, from low-powered processors to high-powered processors to that. Right. So our goal with distributed DTrace is to be able to run the same dscript that we run on all those small machines across however many nodes that is. I didn't count when I started to from the internet. How do we see DTrace, OpenDTrace being used? We expect there to be more kernel trace points because a lot of kernel programmers work on it. So things like IPsec, network link layers should probably have some. More geom and cam trace points. More drivers. There are 75 different sets of debug macros in the FreeBSD kernel and 10,000 calls to device printf and our device drivers. I would like all the device printfs to die in a fire. So my goal is to get things like DTrace to replace that. More user space tools. So we talked about machine readable output. I'd like to see tools like Jeff Roberson's SchedGraph be modernized to use DTrace to pull locking information and scheduler information into, say, flame graphs or something that's more like a software oscilloscope. SchedGraph, lock graphing, looking at the performance of subsystems. Flame graphs are all the rage, so we're going to flame graph all the things. True. And then our goal is to have a development model where we can have a single upstream, similar to OpenZFS and OpenBSM, where there's an open DTrace, and then we can share everything amongst all of the operating systems that wish to consume it. So macOS, Windows, FreeBSD, NetBSD, I'll add OpenBSD later, Linux, Windows, etc. I'm not doing the Windows bit. All right, and questions? Are you ready?
No questions? Oh. Okay, so thank you.
Thank you.